Hi everyone. I receive a lot of message these days. I think I received at least 3 messages asking to discuss um, difference between flipped voltage followers and super source followers. I had already made one video on flipped voltage followers. You can refer to that. So that's a very undergraduate level of introducing what is flipped voltage follower and how to analyze that circuit. Okay, so in this lecture, again I don't have much time, so what I've done here is very briefly, I'm just not going to use mathematics. We will look at the flipped voltage follower and super source follower structures just based on some intuitions, and from that understand the differences between the two, and we'll also compare them to a regular source follower structure. Okay, a regular single transistor source follower. So this here shown here, these two amplifiers or these two structures are called flipped voltage followers. This is an NMOS flipped voltage follower, and this here is a PMOS flipped voltage follower. And these two, this one and this one, okay, I should probably highlight in a different color. So this one here and this one are what they are called the super source followers. And shown here in the bottom here, these structures are called cascaded flipped voltage followers. Okay, or cascade flipped voltage followers. And why are they called that? What is the advantage? In fact, this is something, this structure, this one and this, in fact, this structure is most very popularly seen in LDOs. You will encounter a structure like this very commonly in LDO output stages. Okay, so I'll explain very briefly using some intuitions what are the advantages of a structure like this. Okay, so I'll probably someday, if I get time, I'll float a proper course on LDO. So LDOs had gone through a very interesting revolution in the past 20-25 years. Okay, so we have gone from designing multiple stages. So if you see the early 2000s to late 2000s, so the whole of 2000, the decade 2000s decade, there was this sudden craze for low voltage designs where we had to go for multiple stages of amplifiers to achieve very high gains. Okay, and when you are achieving such high gains with multiple stages, then you have to naturally compensate them. So we had a host of compensation techniques called Miller. Then we had Ahuja. I mean, these are old compensation techniques. We had advanced versions of Miller called nested Miller compensation technique. Then Ahuja was also thoroughly analyzed in that decade, I would say. And then we had dominant pole compensation and non-dominant pole compensation and feed-forward compensation. So all these compensation techniques were very intuitively explored during that decade, okay, to great detail. And someday when I offer an LDO course, I'll cover the history of all of that, and then you can see how well the field itself evolved. Okay, now if you see the current generation of LDOs, if you see most of the industries, which see, I don't have an experience in LDO design for a very long time. I have done LDOs, I think 3 LDOs. Mainly I'm a PLL designer, so the LDOs that I designed were mostly for PLLs. But I have seen how they've evolved for the past at least 15 years. And then you'll see the current generation of LDOs are much simpler, though we use the similar concepts of dominant and non-dominant pole compensation. They're very different in terms of how we approach the design. I would say the structures are very different than what we were used to even just 10 years ago. Okay, so someday when I get time, I'll definitely talk about the LDOs in great detail. I really want to offer a nice course on it. I think there is a lot to go there, explore there. Okay, so I'll come back to that. Now coming back to this discussion, sorry for that small detour. These two structures are what we call a cascaded flipped voltage followers. Why are they called cascaded flipped voltage followers, and why are these called FVFs and these two structures called super source followers? We'll try to find all those reasons in this lecture. So before we go into the actual lecture, I just want to quickly take you through the different kinds of loads that a common drain amplifier normally encounters. The first load that I'm showing here is what we call as a constant current source load. So shown here is a source follower structure, which is typically the output stage of an LDO. Okay, so I have not shown the LDO completely. I'm just showing the final stage of an LDO. So you have a battery voltage. You are supposed to generate a fixed supply voltage VDD from the battery. You will derive. So normally your V battery will be greater than VDD. So in its crudest form, an LDO can be seen as a DC to DC converter. It will convert a high voltage DC to a low voltage DC level. Okay, and the source follower is generally used as the final stage in such load dropout regulator architectures. Okay, so you have different load follower load dropout regulator architectures. I'm talking about a specific case where you have a source follower output to just illustrate you what kind of loads to just show what kind of loads you normally encounter in practice. So shown here is a differential amplifier. If you see, this is a class A amplifier or a class A differential amplifier, and even if your input signals are changing, even if the amplifier is undergoing it's encountering a signal in real time and it's amplifying that signal, the total current drawn from the supply will be constant. That will be same as the bias, the tail current. Okay, the transistor currents individually will change in both the arms, but the total current will always be constant. So such circuits are called class A circuits, whose currents are always constant. So as far as the supply is concerned, it will always see a constant current. Okay, so such kind of loads, I'm calling it as a constant current load. And your source follower will encounter such kind of loads. So that's one example of a load which a source follower can encounter. Okay, so I've shown here, I'm not going into the details of the circuit. I'm just trying to show you the different applications of source followers and the different kinds of loads that a source follower structure can encounter. So if I want to ensure that this node voltage is at VDD, then I have to ensure that the gate voltage is at VDD plus VGS. Now, how do I ensure that? That the negative feedback ensures that there are circuits to do that. Okay, so we're not going to go into details there. Okay, so this is one example of a source follower with a constant current source load. The other circuit here is a classic example of a source follower with a resistive load, wherein here you have, instead of a DC signal, you have an input signal. This is a sinusoidal signal, and you are driving an amplifier, an audio amplifier. An audio amplifier, for all practical purposes, can be modeled like a resistor. Okay, where electrical energy will be converted to thermal energy. So whenever it's a lost energy, right? It's getting converted to some other form. So anytime there is a loss of energy, we model it as a resistor. Okay, so the load can be modeled like a resistor. So what is a resistive load? A resistive load is one where the load current will change proportional to the input levels. Okay, if your input increases, output also increases, and therefore the load current will also increase. It will increase in proportion with the input current. Okay, so that's one example of a resistive load. So here I've capacitively coupled, so the input is the amplifier's output is capacitively coupled. It doesn't matter. There will be a DC current flowing, and when there is an input signal swing at this node, you will be either drawing current, depending on whether the voltage is positive or negative. You will either be drawing current or pushing current into this node. Okay, your load IL load current will be equal to V0 by RL. RL is your load resistance. So this is an example of a source follower structure where it's acting like a final driver stage in an audio amplifier. Okay, where the load is looking like a resistor. Another example of a resistive load is again an output stage of a load dropout regulator, where a source follower structure is used as a final stage in a load dropout regulator. Okay, so we'll come back to what are load dropout regulators in great detail. So right now you can treat them like a DC to DC converter. You have a battery. From that battery you need to generate a clean supply VDD. Generally, if I use the word clean supply VDD, it just means that you need to generate a voltage with a very low impedance. Generally, we know source followers are known to have very low impedances. So it's a structure which is commonly used if you want very low output impedances. Okay, so if you can recall some of the older lectures, where we discussed about source followers, we said a source follower acts like an impedance transformer. The output DC voltage will be very close to the input value. I mean, output AC value will be equal to the input AC, but the impedance will be very different. It will be 1 by GM, okay, which is under the designer's control. So now coming back, here is an example of a same structure like this. So here I've shown it's very similar to this one. The difference is the load is now an inverter, a digital circuit. Okay, a digital circuit, generally I've shown here a very simple example of a digital circuit with a capacitive load. If you have a digital circuit with a capacitive load, every cycle the charge you are delivering to the capacitive load will be, if your input is switching, every cycle you will charge and discharge the capacitor. So the charge you will deliver to the capacitor every cycle will be C times VDD. Okay, this is the charge you will deliver. So this is the charge delivered per cycle. So if you divide by T, I will get the current. So CL VDD by T, this will be your average current, which will be CL VDD times FR. So now if you look at this average current, it is proportional to the voltage VDD here. So if whatever voltage is at this point, the average current drawn is proportional to that. So that is again like a resistive load. So that's what we said, a resistive load is one where the average current should be proportional to the voltage at that node. So this is another example of a source follower where it's used in a DC application. Here there is no signal here. It's used in the final stage of a load dropout regulator, where the load here is a resistor. Another example of a load of a source follower is a very simple example where it happens to be one of the stages of a multi-stage amplifier. You have a multi-stage amplifier and the source follower happens to be one of the stages. So source follower is driving another, this is a common source amplifier. So this is a NMOS common drain amplifier driving a source for a common source amplifier. Now if you see at the source output, the load it sees is purely a capacitor, which is just a drain to gate, the gate to drain, gate to source and gate to drain capacitances, which is what it's going to see. Okay, so I'm not considering the exact loads, but I'm just giving you an intuition that typically if you're driving the gate of a device, you will normally see capacitive loads. Okay, so here it is capacitive loads. So totally I've shown you different examples of common drain amplifiers or source followers, where the load can be a resistor, load can be a capacitor, and load can also be a current source. So I have shown you 3 different examples where load can be current source, capacitive or resistive. Okay, a current source load is constant. Okay, it's like a capacitive load. You can treat it like a capacitive load. It's always constant and independent of the average current is independent of the output voltage. Resistive load on the other hand, the average current is proportional to the output voltage. So now we have laid down the basics. I've just given you an idea what kind of loads a common source amplifier can normally encounter. Okay, I've not gone into details. I've just given you an idea about different applications. It can be used as a final stage in a load dropout regulator. It can be used as a final stage in an amplifier here where signal is present. Okay, it can be used as one of the intermediate stages of a multi-stage amplifier. Okay, so in all these cases it sees different kinds of loads. So now I'll first quickly try to analyze a source follower architecture, the DC characteristics of a source follower architecture for different loads. For a capacitive or a constant current load, if you see this is a capacitive load and it's same as constant current load, I'm drawing the DC characteristics. If I'm drawing the DC characteristics, you can directly see your output voltage minus the input voltage is equal to VGS of this MOSFET. Okay, it's simply equal to VGS of this MOSFET. The VGS of the MOSFET, if you expand it, it will be square root of 2 IB upon beta n. Beta n is mu n Cox W by L. So this is mu n Cox W by L plus VDN. So if I ignore channel length modulation, I'm ignoring channel length modulation, which means there is no VDS dependence on the drain current. I'm also ignoring body effect, which is I'm assuming gamma is 0, lambda is 0. If I ignore both, then if your bias current is fixed, these two values are fixed, which means your VGS is fixed. So therefore, if your bias current is fixed, it's going to act like a constant value. So this VGS will be constant. If VGS is constant, then V naught is equal to Vi plus some constant. So you will have the characteristic will look something like this. So here I'll not go into details. So if you sweep your input, initially when your input is 0, the MOSFET doesn't conduct any current. You need at least VT volts. Once you start applying VT volts onwards, the device will slowly start conducting current, and when Vi becomes equal to 1 VGS, the current will be equal to VB. Okay, so I should show some slight nonlinearity at the origin. After that, it will look like a perfect straight line because your VGS is always constant. Your current is not changing in the MOSFET, which means as you increase your gate voltage, source voltage should also increase by the same amount. Okay, this relationship will hold true as long as the device is in saturation region. So when your gate voltage goes higher than a VT, than the drain, then you, of course, it goes into a linear region and all that. But right now we'll assume that your input doesn't exceed VDD. So for all practical purposes, I can assume that it's going to be always in saturation region. So the gain will always be close to 1. Okay, so this is assuming lambda is 0, gamma is 0. It's a perfectly linear amplifier for a capacitive load. At the moment I add resistive load, we know that the load current will be function of the finite output voltage as well. So now if I write the equation, V0 minus Vi will be equal to VGS, and your VGS depends upon, now if you see the current flowing through the MOSFET comprises, let Im be the current, it is the sum of two currents. You have, if you apply KCL at this node, it will be the sum of the current source IB and the load current IL. So your Im equals IB plus the load current IL. It's a sum of two currents. Now IB is constant, but IL changes with the output voltage. Okay, so you have IL here. I've written an expression for the VGS here. IL will change with your load current. Okay, sorry, output voltage. So here you will have a dependence on V0. Okay, so your result will look something like this. Your V0 minus Vi will be equal to root of 2 constant bias current IB plus V0 by RL divided by beta n plus VTN. So here again I've ignored channel length modulation and body effect. Okay, if you include both, then those two will also be sources of nonlinearities. Okay, you will get additional sources of nonlinearities. So in fact, even if I take a constant current source load, if I consider channel length modulation and body effect, you can immediately see that you will end up getting a nonlinear relationship because your VTN will depend upon square root of V0 and all that. Okay, and you will have another multiplying factor which will be proportional to VDD minus V0. Okay, the drain current depends upon 1 plus lambda VDS. So if you include that factor, you will get an additional source of nonlinearity. So I'm ignoring all of that here to simplify the problem, okay, to show you what's happening in the circuit. So if you consider the output, the load current as well for a resistive load, we see that your V0 minus Va is proportional to square root of V0. Okay, so now we have a nonlinear dependence. So this is the source of nonlinearity. Even if you ignore channel length modulation and body effect, for a resistive load, fundamentally the relationship between V0 and Vi becomes nonlinear. Okay, and you can see that from this equation. Or you can see that as your input voltage is increasing, if you have a large input signal voltage level, your load current also, output will also increase, which load current will also increase. If your load current increases, your VGS will increase because the MOSFET has to carry that current. How will it carry more current? By just increasing its VGS, because you cannot change its W by L. Okay, the only way you cannot change it on the fly. Okay, so once you freeze your design, then the only way you can increase your current in the MOSFET is by increasing its VGS. Okay, so that VGS will increase. So that's what I've shown here in the curve. As you increase your input signal levels, what will happen? The difference between your Vi and V0. So this is the ideal characteristics. V0 equals to Vi plus constant. This one here is including the nonlinearities. As you increase your V0, the difference between V0 minus Vi. So this is V0 minus Vi, previously was just a constant. Okay, it was a constant. It was like this. But now it will increase with proportional to square root of V0. Okay, it will increase like this, square root of V naught. Okay, so which is why you see this difference. So this is the source of nonlinearity. So this is the problem of nonlinearity in a common drain amplifier with a resistive load. Okay, this is well known. I mean, these are not new things. These are well known for circuit designers. You'd encounter nonlinearity in the presence of resistive loads. Another point I've discussed, if you look at this structure, this is a NMOS source follower. If your input is positive, if you're, I'm directly, this is called DC coupling. So here the load current is always what in a sourcing mode. I mean, the MOSFET is always in a sourcing mode. It's always sourcing the load current into the resistor. I can also have a load in this format where current is being sunk in. Okay, it should be able to sink the current as well. Okay, and this is very common. I don't have to connect it to VDD. If I just capacitively couple my load, okay, and if I, then you will have a signal which is going to go both positive and negative. So whenever it's positive, you will draw current, push current into the load. Whenever the voltage across the resistor is negative, you will pull current from the resistor. So these things will happen. Okay, so you can have currents flowing both in either directions. When it comes to sourcing current, ideally, as long as your VGS allows, as long as your VGS is large enough, okay, you can actually keep it can supply current all the way from 0 to the load. It can supply all the way from 0 till IL max. So IL max corresponds to the maximum voltage output can go to divided by RL. Okay, so it can supply all that current, and that it will happen by increasing the VGS. But if you have to sink current, if the MOSFET has to sink current from the supply, then you can see if you write KCL at this node, the current flowing through the MOSFET is given by I bias minus I load. So when your current is flowing through this resistor, because the sum of the two currents is constant, the current in the MOSFET has to decrease. Okay, IM will be equal to IB minus IL. So when your load current becomes equal to the bias current, then the MOSFET's current will become equal to 0. So you cannot, after that your MOSFET is in cutoff, so you cannot expect any more amplifier behavior. So there is a limitation. When you have to source currents, you cannot source a current greater than the bias current. Again, these all points should look pretty intuitive to most of you. I'm just stating it for the sake of continuity. Okay, just completeness. Okay, so this is another example of a source follower. I'm just showing it will also have a nonlinear characteristic, and you can work it out and check for yourself. As you increase your load current, the VGS will decrease for the MOSFET. So here I have shown that the gap will decrease. If you are sourcing current into the MOSFET, your VGS will decrease because your current through the MOSFET will decrease, and because if you see, the current through the MOSFET is IB minus IL. So as you increase your IL, your characteristic will come closer. Okay, so maybe this is not a, yeah, so maybe this may not be a good representative. The curve may not be a good representative what I've drawn, but I just wanted to stress this point. If your load current is very high and it is sourcing and it is sinking, and MOSFET is supposed to sink that current, then the VGS of the MOSFET has to decrease. Okay, so then Vi minus V0 will be closer to each other, and vice versa. So that's something to keep in mind. So I've shown here an example of an PMOS based source follower. A PMOS based source follower by design, it will do the inverse of what an NMOS source follower did. The output DC of a PMOS based source follower will be greater than the input DC. Okay, so your V0 minus Vi will be equal to VGS. So if you see in these equations, oh sorry, I've written it here, it is Vi minus V0 is equal to VGS here. I think I've made a mistake here. So this one is Vi minus V0, Vi minus V0. So your input DC will always be greater than the output DC for an NMOS source follower. For a PMOS source follower, your output DC will be greater than the input DC. So V0 minus Vi will be equal to VGS. Again, all the same rules that we discussed will apply for this one as well. Okay, so I think I'm right here. So if Vi is 0, V0 should be, Vi is 0, your V0 should be negative. So that's right. So this graph is correct, but I think I made a mistake. I'm sorry. It should be Vi minus V0. So now we'll come back to this. What we discussed is, we said that in the presence of resistive loads, a source follower becomes nonlinear. Okay, a source follower becomes nonlinear. So if I want to linearize a source follower, what can I do as a circuit designer? As a circuit designer, if I want to linearize a source follower, I'll play some of the simplest tricks in the book. What is that? I'm just going to increase my bias current and increase the GM of this MOSFET. How does that help me? How does this help me? Okay, so all I need to do is, even if my load current is changing, even if my IL is changing, I need to ensure that your V0, Vi minus V0 is constant. Vi minus V0 is nearly constant. And how do I do that? I can simply ensure that your IB is much greater than the load current. Okay, if I ensure that IB is much greater than the load current, your VGS will be mainly dominated by the bias current. Okay, so load current will not have much impact on the VGS. So you can also look at it other way. Your load current, if let's say your load is changing, or I just vary my ZL, or your output is changing, the current that you have to supply is delta I to the load. Because of a change in the voltage, you have to supply a current of delta I. That current has to come through this MOSFET, and to accommodate this current delta I, assuming that it's a very small current, I can approximately use a small signal model and say the change in the MOSFET's current has to be equal to GM times delta V. So change in the VGS has to be delta V. If I choose a very large IB, my GM keeps increasing. So your delta V equals delta I upon GM. Okay, as your GM tends to infinity, even if your delta I is finite, I can push delta V to 0. So that's what I'm doing. When I say GM tending to infinity, all I'm ensuring that is the bias current of the MOSFET IB, I'm tending it to infinity, very large, much larger compared to delta I. When I ensure that, the change in the voltage will come to 0, nearly 0. So this, if I try to blow up the source follower's current to infinity, or its transconductance to infinity, then I'm achieving almost a super source follower kind of a behavior. So if I want to do that, I have to blow up I have to make its current infinity, then I get a perfectly linear characteristic where Vi minus V0 is always a constant. Okay, so I can achieve a linear characteristic. So this one is for a finite GM or a finite bias current, where your bias current can be smaller or comparable to the load current. This characteristic here is your bias current is much larger than IL, so it looks like an infinite GM device. So you can that's one way of linearizing using circuit design. Now we will see in a few moments, there are circuits which will linearize this without resorting to an infinite current. So one such example is what we call a flipped voltage follower. I've shown here an example of a flipped voltage follower. Sorry, I'm using a PMOS follower to illustrate the point. You'll understand why am I doing that in a few moments. But if you see, a flipped voltage follower has a source follower device. In addition to that, you'll also have a feedback device. You also have a common source amplifier in feedback. So this is a common source amplifier. If you see, the gate voltage of this, the drain voltage of the source follower, previously is drain voltage of source follower is always held at a constant voltage. Okay, that's not changing at all. Now what we do, instead of that remaining constant, we are taking that and feeding it to the gate of another device. Okay, when I do that, we'll see what happens right now. For capacitive loads, yes, of course, I'm increasing the input, output will also increase because your current through this MOSFET is constant. Okay, your current through the MOSFET is constant, so which is expected, V0 minus Vi. So this graph is not correct. So your V0 equals Vi plus VGS. or V mod of VGS, I'll write because it's a PMOS device. So that will be root of 2IB by beta n, which is again a constant. Even if I'm changing Vi, your V0 will also increase linearly. Okay, so the graph should look something like this. So when Vi is 0, V0 is 1 VGS. I'm just drawing this graph here, so it's not ideally so it will look something like this, the graph with a slope of 1. Okay, so let's not worry about when it will saturate and all that. I'm just showing that it's going to be a gain of 1, near constant gain, a perfectly linear amplifier, which is what we already saw for a regular source follower with a capacitive load. So there was no problem with DC characteristics of a regular source follower with a capacitive load. The problem came when we had resistive loads. Now I'll show you, when you have resistive load also, we can get a near constant or near linear characteristics here. So if I assume, let's have a resistive load R here, RL here. Okay, now look at this structure. The current through this PMOS is always constant, it's always IB. Okay, now the current through the upper PMOS is IB plus the load current. If you apply KCL at this node, with even before I go to analyze the circuit, I can simply say the load current has to come from the upper PMOS device. Okay, that will carry the current of IB plus IL. Now just for comparison sake, recall your NMOS device was carrying this current. So we had IB and the load current IL, and this NMOS device was carrying IB plus IL. Now you have a PMOS device, which is a source, which is not even a source follower device, which is a common source device, which is carrying this current. Okay, and the VGS of this device is always constant. Okay, if we'll ignore channel length modulation and all of that right now, if I ignore all of that, the entire load current has to come from the upper PMOS device. Right? There is no other, because I'm forcing the current through the lower PMOS device to be constant. Therefore, V0 minus Vi, which is VGS in this case, is always a constant. V0 minus Vi is always a constant. Okay, because your IB is constant in this device. Now you see, I've gotten a very linear characteristic without spending infinite current. Okay, without spending infinite current, I got it. I've just shown you an example of a PMOS based flipped voltage follower amplifier with some modifications to it, and I was able to achieve a near linear characteristic for a resistive load as well. Okay, because that current, the load current, is entirely flowing through a PMOS. How is that flowing? For example, if let's say this node voltage, because let's say you connect a load resistor suddenly to the circuit, you are going to draw some current through the load resistor. So this node voltage will dip, it will decrease. So immediately, if this node voltage decreases, see this guy will act like this structure will act like a common gate amplifier. So you have a PMOS whose source is changing. Immediately this node will also go down by a much larger value because it's an amplified version here. It's a common gate amplifier. So when this goes down, the gate here goes down, so the drain current of this MOSFET will increase. And the process will continue until the drain current of this MOSFET becomes equal to the load current. So what will happen? The source voltage here, the gate voltage here will slightly change. So remember, we said that the NMOS device's VGS has to change to accommodate the load current, right? For the load current has to flow through this NMOS, so its VGS had to change. But now it's going to flow through this PMOS, so its VGS will slightly increase. Okay, it will increase by delta V to accommodate for the load current. But if you see the source follower device, that VGS is constant. That's not changing at all. And therefore, your V0 will be equal to Vi plus a constant, which is a linear characteristic. So I've gotten a near linear amplifier using this. I'm again ignoring channel length modulation and body effect, but I've gotten a near linear characteristic for a resistive load. The same structure can be compared, can be designed using an NMOS source follower as well. So the same way, what am I doing? The drain voltage of this MOSFET, the source follower, I'm feeding it to the a common source amplifier. Here it is PMOS common source amplifier. And I've connected the load here. The load current flows this way. Now if you look at this architecture, it's the same as this one, except that the source follower device is an NMOS device. That's it. It's an NMOS device source follower. The output goes to a common source amplifier in feedback. So this is the feedback loop. Okay. So this structure is identical. You can quickly see that. Imagine you suddenly connect a load here. So it's going to draw some current on this node. Whenever you draw some current on this node, the source voltage will go down. If the source voltage is going to go down, this will go down by a much larger value because it's amplified. This is a common gate amplifier. It will amplify it. And this delta V will increase and the MOSFET will start, the current through the MOSFET will increase. And this process will continue until the current of this MOSFET becomes equal to IM plus IL. Okay. So here if you see, I've used two biasing currents. So previously in the circuit there was one bias current which was biasing both the MOSFETs. Here you have a current IB to bias the source follower device and a current IM to bias the PMOS device. So the total current, I've just shown one current source on the shared node. At this node I've shown a current source of value IB plus IM to account for both these currents. These are the bias currents. Now the bias current in this device will always remain constant even as the input is changing. Even as the input is changing, it will remain constant because I'm forcing, the drain is forced. It's fixed to a constant current. I'm forcing a constant current through the drain. Okay. So by design, I'm not letting it change. So any current in the load has to come from the PMOS device itself. Okay. So this device behaves exactly like a source follower. If you see, both these devices are very similar. Why are they similar? Because they both are able to source current to a load, very similar to how an NMOS source follower can do. They both can source currents to a load. Okay. And they both have similar properties. They have very linear characteristics. They both can source current. And in both the amplifiers, in both these structures, it is a PMOS device which is going to carry the current, the load current. The load current, the source follower device does not carry the load current. Okay. In this structure, if you see, your Vi minus V0 is VGS, which is a constant. Okay. The difference between these two structures, this amplifier versus this amplifier, is that I can set the GM of the PMOS, the current carrying device, which is the PMOS, the common source PMOS device, independently. Okay. Here it is, both the currents are, by design it's forced to be same. Bias currents are same. Here I can set them independently. Okay. So that's the change in the design here. Now what I've done here, if you observe this device, I've done something very interesting here. I've just modified the architecture and used negative feedback. I'm burning finite power. IB plus IM is finite current. And I've achieved a near linear characteristic. V0 equals nearly very linear with respect to Vi. Okay, for resistive loads, I've achieved a near linear characteristic, wherein the VGS is always constant even if your input is changing. Okay. The V0 minus Vi, I'm doing level shifting. I'm shifting the DC levels between V0 and Vi, but that VGS is independent of the load current, which manifests as a near constant gain or a very linear characteristics, very linear input-output characteristics or transfer characteristics. That should sound very interesting to you because I have now achieved something that I can achieve in a regular source follower by burning infinite current. So what would you call an amplifier with a slight modification is going to behave like a source follower with superpowers? I mean, superpowers meaning its current is infinity. Okay. It's almost an infinite current. So it's behaving like a source follower on steroids, which it has very large current. It's behaving like that. So this structure is what we call a super source follower. A source follower with superpowers, it's like a super source follower. Okay. I mean, of course, we can do small signal analysis and show that it translates to lower output impedance, higher short circuit transconductance and all that. But it just boils down to this. If you see, I've reduced this structure to a source follower with an infinite current. Okay, that's how I'm assuming channel length modulation is infinity. Okay, channel length modulation is 0. There is no channel length modulation. Okay, then I can claim it behaves identical to a source follower with an infinite current, NMOS source follower with an infinite current. So that's what I've just used an analogy here. Superhumans often tend to undergo, especially these are of course imaginations of humans, would often have properties which are considered non-human. Okay, regular humans would probably undergo non-elastic collisions with bullets, but superhumans can undergo elastic collisions. So here Superman bumps off bullets as though it's nothing. Okay, so comparatively, these structures, both these structures behave like super source followers when you compare it with a conventional source follower. But in the literature, only this guy is called super source follower. Okay, this guy is called super follower because if you see, it's identical to this. It's the same NMOS source follower where your DC level shifting to a lower value. Okay, it's called super source follower. But ideally, both have this property of giving you very low output impedances and very high short circuit transconductance. Okay, but the difference here is that if you see functionally, this structure is very similar to an NMOS source follower because it can also supply source current to a load resistor. Okay, or sourcing current to a load resistor. So functionally it's similar to that. So but you have a device flipped. Here it's an NMOS device, it's flipped to a PMOS here. So then it's a flipped voltage follower device. Okay, so I'm not sure of the exact nomenclature, but if I were to name it, I would just name it this way. It's behaving like this, very similar to this, but with the device flipped. So then it becomes a flipped voltage follower. And the other one here is a it's exactly same as an NMOS because it's the same. Your output DC is lower than the input DC. Okay, and but I have a GM very high short circuit GM, or I can say that the characteristics are linear. The load current is not carried by this MOSFET at all. You have another device which is carrying this. Okay, so that's called a super source follower. Okay, so that's the difference. So flipped voltage follower and a super source follower. So we'll finally towards the end of the lecture, I'll try to compare the differences between these two architectures. But right now, I'm just introducing the name of these two structures. So, okay, now that we have introduced flipped voltage followers, I'll just go a little bit deeper into it. I'm not doing frequency response analysis right now. I'll do a frequency response analysis later. But right now, if you look at this architecture, I said that, when we were discussing, we said that the current through this MOSFET is always fixed. Okay, and if the current through this MOSFET is fixed, that's why we are getting the linear characteristics. But if you see a source follower, a normal source follower, the drain node is always calm. There is no variations on the drain node voltage. But here if you see, the drain node voltage can oscillate significantly, in fact. Okay, not significantly, it can oscillate. It can have large variations. So if your gate voltage goes positive, your drain voltage will go negative. Source voltage will go, see if you see, you can show that the gain from here to here is close to 1. So we'll discuss all these things later. Okay, here it will be 1 by GM or not. You can show all those things later. So what will happen is you will have a slight decrease in this node voltage. So your drain voltage is actually undergoing a signal change. So it's not truly a source follower device. A source follower device is one where drain should nearly remain constant. And that can be achieved by using what we call as a cascoded flipped voltage follower structure. So what I'm going to do here is I'll use an NMOS device with a fixed bias voltage at the gate terminal. Okay, and I'll just modify the device and I'll connect the drain of this device to the gate of this MOSFET. Now what am I doing with this? So let's say this node voltage changes. Your drain voltage changes, the currents are all constant here. Now you are going to generate a current GM delta V, which will flow through this device like this, because these currents this sum of the two currents has to be constant. They will flow through this, and this node will undergo the signal variations. Okay, so this node will undergo the signal variations. If input is changing in this way, this will change in the opposite direction because it's a common source amplifier. I mean, there is gate to source, gate to drain, there will be a 180-degree phase inversion. So it will undergo this change, and then otherwise it's going to behave very similarly to this device. The only difference is now the drain voltage, because I'm forcing the current through this device to be constant, the VGS of this device is constant. If the VGS of this device is nearly see, again, when I say it's constant, I'm assuming it's nearly constant. Okay, it's nearly constant, then this node voltage will be VBN minus VGS, which will also be constant. So I have achieved a behavior very close to a common drain amplifier, with the drain node voltage is remaining calm here. It's not changing much. So if you see here, I've just accounted for all the currents here. So I1 current is flowing through this, IB is current flowing through this. I have to bias, this is the tail node. I'm biasing it with the sum of the two currents. Okay. Now you can also look at it this way. So let's say to accommodate a load current, the gate voltage has to increase by delta V. So which means this node has to change by delta V. Now we know, if you recall from cascode amplifiers do have a property called of node shielding. So if your drain node voltage changes by delta V, the source node voltage will change by delta V by A. Okay, it tries to shield. That's how we achieve high output impedance, if you recall the voltage lectures. Okay, so that's what we are doing here. Even though this gate voltage is changing by delta V, the source voltage will change by much smaller value, delta V by A times, intrinsic gain times, much smaller value. So this device, it's actually it's the cascode device. It's like acting like a cascode device by shielding your drain node from the signal variations. Okay, so it's decreasing the signal variations. Therefore, this is approaching closer to behavior to a common drain amplifier. Now, this structure is very popularly seen in the modern low dropout regulators. You will see the output structure is very similar. I mean, you will have some more modifications depending on how they compensate it, but this is a very commonly seen structure. So this is called as a cascode flipped voltage follower. It's a flipped voltage follower. We are adding a cascode device to ensure that the drain node voltage doesn't see much change. Okay, I'm shielding this node by doing this. That's it. So otherwise you can derive and show all the output short circuit transconductance, output resistance, and all that remain the same. Okay, so remember, anytime I'm making a change, I'm introducing more nodes. Okay, so conventional source follower had just one node, input and output. That's it. There was only one output node. Here you have two nodes. There is one internal node here. In this circuit, we have three nodes. So there is one node here and another node here. Of course, there is a final output node. I'm not including the input node. So you have three nodes in the circuit. Okay, and there are two internal nodes. So anytime we add additional nodes, you have problems of poles, non-dominant poles. So we have to worry about stability. That's a later problem. Right now, I'm just introducing you to the idea from a DC characteristics point of view. So you will see this structure. This is often called a cascoded flipped voltage follower. So finally, I have discussed what needs to be discussed. So we began with the goal of understanding the difference between a flipped voltage follower and a super source follower. I think I've explained you the difference. They both are very similar. In fact, they both can be called as super source followers because they give you very high output, very low output impedances and near linear characteristics for resistive loads. Okay. The difference between the two comes in the characteristics, because the super source follower behaves like, the DC characteristics is identical to an NMOS source follower. Okay, this guy on the other hand, even though its behavior is identical as far as the load is concerned, its DC characteristics is not identical. It behaves, it's similar, but with the device flipped. NMOS is flipped to PMOS. So this will be a flipped voltage follower. And this guy here is a super source follower. It's identical to a regular source follower, but with its output impedance lowered and GM boosted and all that. Okay, so we just showed that you can get near linear characteristics, or when I say near linear, using feedback, we are trying to achieve a GM of infinity. That's what it means. When I say near linear, I mean that. Okay, you can show that if I assume channel length modulation to be infinity or 0, lambda equal to 0, you can show that the loop gain for the circuit will be infinity. Okay, you can easily show, assume ideal current sources, you can show that it's infinity. Okay, so that's how you get a GM of infinity using negative feedback with finite current sources. Okay, that's why I said that it's a near constant. Okay, this the difference between input and output is near constant, or the slope is 1. Okay, so now for the commonalities, I mean if you see for capacitive loads and small signal wise, both these circuits are the same. Flipped voltage followers and super source follower are the same structure. Capacitive loads, the poles. Here the other difference, the other major difference between the two, of course, the one obvious difference is the output DC is lower than the input DC. That is one big difference. The other big difference is you can set the current for this common source device independently. In a flipped voltage follower, it is forced to be same. The bias current is forced to be same. See, here I'm assuming it depends on how you connect your load, but I have the power. If let's say RL is infinity, if there is no load, I can set the bias currents independently. That is an additional degree of freedom you have in super source followers. Okay, so that's it. And I think I've shown here a flipped voltage follower and super source follower equivalents for an NMOS a common drain amplifier. It's just for NMOS common drain. The flipped voltage follower will be based on NMOS devices. Okay, for a PMOS source follower, it will be based on NMOS devices, and it's very similar. If you have a load here, it is this device which is going to carry the current, the lower device, the common source device, which is going to carry the load current. Okay, so it will be able to easily carry a source, a sinking. It will be able to sink current this way. Okay, if your load is connected to VDD, this amplifier would be a much a preferred choice. So here this will be a super source follower equivalent of a PMOS source follower, where your output DC will be greater than the input DC, and you get a near linear characteristics, input versus output. And how do we achieve it? Using feedback. We have used feedback to achieve that characteristic. Okay, and I've also shown a cascode flipped voltage follower for a NMOS version. The same way, how did we do? We wanted to shield the drain node here. Okay, to shield the drain node, I just introduced a cascoded device, a common gate PMOS amplifier. Okay, the opposite of what we did with the PMOS flipped voltage followers. So here I've shared this node becomes the tail node here, and instead of directly connecting the drain of this MOSFET to the gate of the common source device, I connected through a cascode device. I put a cascode device in between, so this becomes the drain node is connected through another PMOS device. So here, if this changes by delta V, this node will change by delta V by A. It will be a much smaller variation. So this will behave very close to a common drain amplifier. Okay, so its drain will also be calm, and both input and output will change. So it's truly a common drain configuration. Okay, this is what we call a cascoded flipped voltage or cascode flipped voltage follower. So this is something you will normally see in the literature. Okay, so that's it. So if you do have any questions, do write to me. I'll definitely try to answer the questions. Okay, thank you.